greatest contribution to come from India is the conception of zero as a number. And that actually was done in the context of general development of algebra. Algebra is essentially the manipulation of unknown quantities, of variables. And this was a concept which really developed in India, but not exclusively in India. It was already, it's also being developed independently in Greece, and earlier even in Mesopotamia, people had some idea of algebra. Though it's only after, basically it's, even Euclid had not really formulated algebra axiomatically, much later that it happened. But in any case, someone like Brahmagupta, who lived in the 7th century, certainly was an algebraist. He knew he was handling variable quantities and how to manipulate them. And maybe even Aryabhatta, already a century earlier, who lived in the 6th century, already had this. Usually people, at least some people, think that the idea, concept of zero and the place value system evolved in the 4th or 5th century, before Aryabhatta. The dates in history, in Indian history, are always disputed. They never, most scholars don't come to any consensus on that, and it's not surprising that there's no consensus on this. There's something called the Bakshali manuscript, which is now lying in Oxford or Cambridge Library, which has already indications that the place value system was used, and that some people date back to 4th century. It's not yet widely accepted, but a good number of people seem to believe it belongs to the 4th century. That's why we place zero in the 4th century. There is, for example, there is no inscription of zero in India anywhere till the 10th century or 9th century. There's a temple in Gwalior where the number 270 is written with using zero. That is the earliest conception of, record of zero in any inscription. There is actually an older inscription in Cambodia where zero figures. And in fact, it's older, it goes back to the 6th or 5th century or thereabouts. And there was an immediate claim. The Chinese have their own chauvinists who immediately claimed maybe zero came from China. But unfortunately for them, the rest of the inscription in that particular inscription is in Sanskrit. So there's no, anyway. So this is it's more or less certain that zero was invented in this country, and that probably is the greatest achievement. I would say it's the greatest achievement in science in general. Without that, no further development of science would have been really possible, serious development of science. Well, so there was this great development, but one of the things which is curious about our civilization, we don't seem to remember names of the people who contributed greatly. We know, of course, Aryabhatta and Brahmagupta and some later people, but there must have been scores of others. We don't know who invented the place value system. I don't know why this happened. Maybe it's a philosophy that what matters is the work, not the man, or the woman for that matter. So maybe that's a philosophy, but I don't know. But the kind of praise people heap on others these days, politicians especially, one suspects that there's not enough adequate realization of the importance of great work done by these people. Even people like Aryabhatta and Brahmagupta, their names were not really widespread, not widely known. Someone like Archimedes in Greece was widely known. Something like that didn't happen in this country for whatever reasons. Well, and then, as I said, Brahmagupta is a well-known name, internationally well-known name, and so Aryabhatta. They are considered greats, and they certainly produced great mathematics in their time. But it must be pointed out that it was great at that time. You cannot, that they conceived of those ideas at that time is certainly great, but what they did at that time is now in school textbooks. So it's not, you cannot say it has great impact on modern mathematics. No way. It was certainly an outstanding achievement in their times, but one must have some perspective on this. And after that, there was another great name, which is not so well known even in this country. This was a man by name Madhava, who actually had discovered the calculus 3 centuries before Newton. But Newton went much further. There's no question about it. And Madhava's motivations were not Newton's. Newton's motivation is essentially to understand motion. So it essentially comes from natural sciences, so to speak. Madhava's motivation is not clear what it is, but I, from my limited knowledge of what he has done, think that it was, in some sense, he was trying to effectively compute certain things. That is, he wanted to, for observational astronomy, it's important to know the values of sine function or cos function, generally trigonometric functions for different values of the angles. You have to know. And for computing, he wanted accurate measurements. He wanted to find out accurately what it is. And this could be achieved by expanding them in infinite series and calculating sums up to large. Of course, you can also experimentally calculate by fixing degrees and so on, but this was a much more effective way of getting the values as close to the correct as possible. He also, among other things, he had the so-called power series for various trigonometric functions like sin x, cos x, and things. These are things which Madhava had with him. And then he also had, for the value of pi, he had the so-called formula, so-called infinite series, which has been called Gregory series. In the recent past, some Indian mathematicians have, of course, insisted on calling it Madhava Gregory series, and correctly so. But we took to, some of the brighter Indians did take to Western mathematics avidly, and we started producing good mathematics towards the end of the 19th century and early 20th century. The biggest name, of course, is Srinivasa Ramanujan, whose work is still of great interest, and I have a picture of Ramanujan there. But there is one misconception about Ramanujan in general among the public. There's a feeling that it was a wild flower which bloomed in the desert with nothing else was around. This is not quite true. There are many other Indians performing at a very high level in mathematics in his days, but not quite of his standing. But for that matter, nowhere in the world were there so many people of his standing. There may be a dozen other people who stood shoulder to shoulder with him in terms of achievement. But in India, there were people who were contributing to mathematics, which was substantial. The contribution was substantial. Ramanujan's contributions, of course, was more than just substantial. It was going to have an effect for the future of mathematics in many different ways. Anyway, that is Ramanujan for you. As I said, there were contemporaries of Ramanujan who were contributing very significantly to mathematics. And I want to say a few words about them. Once again, I will not be able to say what mathematics they did, except in one case, where I will go to some length, which will tax you a little bit, but not too much. But it requires only a high school background, nothing more. I can talk about it, but others I won't be able to. But let me introduce some of them to you. This is Shyamadas Mukhopadjyaya. 1866 is when he was born. Ramanujan was born in 1887. So he was something like 11 years older than, 21 years older than Ramanujan. He was the first person to produce work which was recognized as important internationally, and is the first piece of work in what is known as global differential geometry coming out of India. He proved what is now called Mukhopadjyaya's four-vertex theorem. It's known as Mukhopadjyaya's four-vertex theorem. The theorem, once again, it requires a little bit beyond school mathematics to understand the statement, but nevertheless I'll make the statement. Some of you will certainly understand. The mathematics people here will understand, but, well, the rest I don't know. Anyway, so now, here is another man who was a contemporary of Ramanujan, Anandarao. Anandarao was a student of Hardy, the same Hardy who was a collaborator, mentor, everything for Ramanujan. He was a student of that. He came from a fairly well-to-do family, and the family sent him to Cambridge rather than somebody supporting him and so on. The family itself was able to support him. He went and studied in Cambridge and did remarkably well there. He worked in an area called summability, which is, it used to be a very important central area of mathematics in those days, no longer, because everything has been worked out more or less. There are problems left, but nothing which will excite many mathematicians. But in his days, it was an important thing, and his contributions were very, very good. And among other things, he won the Smith Prize, which Ganesh Prasad didn't make. Anyway, he came back to India and became a professor at Presidency College in Chennai, not the famous Presidency of Calcutta, but at Chennai. And one of his theorems figures in a treatise of Hardy's. There is a treatise of Hardy called Divergent Series. In mathematics, you come across many infinite series. Some of them cannot be summed up in a reasonable way, cannot make sense of it. But you can interpret summation in some different ways, and that's what all summability is about. and that is the kind of thing that Hardy was interested in, and Hardy was a big expert in. And in Hardy's book, a definitive treatise on this, there was this paper of this theorem figures, Anand Rao's theorem figures. So it's clear that all these people have had international impact. Pillai has a definite place in the history of mathematics. He solved what is known as the variance problem. I'm going to say something about the variance problem because it's a problem which you can understand what it's all about. So I'm going to say something about the variance problem. About Vijayaraghavan, I will not be able to say much because his work is much more technical, except that I want to tell you that there is something called Piso-Vijayaraghavan numbers, something named after Vijayaraghavan, which shows that there is some very interesting work due to him. Anyway, so here is next two mathematicians I want to mention. One is Meenakshi Sundaram, arguably the most gifted of that generation, and the other is Chandrasekharan. Meenakshi Sundaram did some work in differential equations. She developed what is known as asymptotics of the heat equation. The heat kernel, as they call it, has an asymptotic expansion. I will say something about it because it's an important piece of work and had impact much later. It was applied to give a proof of an important theorem much later, way later, sometime in 1975. And I'll come to that. I'll say something more about him. Chandrasekharan, once again, his work is not something which can be easily accessed. Even the statements cannot be understood of his theorems, but he did prove some important theorems. He worked in what is known as summability, not abstract, but Fourier series, and something about what are known as Dirichlet series. Those are important pieces of work which have also had impact. In fact, some of his work done in collaboration with a younger man whom I will mention has been used recently, within the last 2 or 3 years, by people working in the frontiers of number theory. One of them in India, a young fellow by name Ritabhrata Munshi, who is now at ISI Calcutta. Anyway, but Chandrasekharan's even more important contribution was that he built an outstanding school of mathematics in Bombay at the Tata Institute of Fundamental Research. In the 60s, late 50s and beginning 60s, he joined the Tata Institute in 1949 when he started developing a graduate school and things of the kind. In the early years of 1960s, the school was well established and was recognized as one of the outstanding centers internationally. It could hold its own against institutions like the Institute for Advanced Study in Princeton or the Mathematics Department. And now I come to mathematicians wholly in India, working in India. Seshadri got his doctorate working at the Tata Institute of Fundamental Research. It's a doctorate from Bombay University. After that, he had a stint as a postdoc in France, during which time he proved two important results which are to this day of interest. One settled a well-known conjecture of a great mathematician, Serre, in a special case. It's difficult to describe that. It's an algebra, in commutative algebra. It's a conjecture. And those of you who may know some commutative algebra, the conjecture was that on a polynomial ring over a field in any number of variables, every projective module is free. And Seshadri proved it for polynomial ring in 2 variables. That is the first breakthrough. Some 20 years later, people were able to prove it's true for all polynomial rings, but 2 variable thing was a big step. And in any account of this about modules or polynomial rings, Seshadri's name will figure. Say he proved it in the case n equal to 2, kind of thing will be there. And that was Seshadri. And Seshadri had from college days, was always with another outstanding mathematician of the century, M.S. Narasimhan. Narasimhan and Seshadri were fellow students in Loyola College in Chennai. And they came and joined the Tata Institute at the same time, same year. And they continued to work with each other in many ways. But Narasimhan went in a completely different direction. And he was also sent to France as a postdoc for some time. And around the same time, 58, 59, he proved a very beautiful theorem known as regularity theorem, analytic regularity for partial differential equations. For those of you who may understand something, he proved that for any linear elliptic equation with analytic coefficients, you have if all the coefficients are analytic, then any solution is necessarily analytic. So called analytic regularity of elliptic equations. He proved that theorem. And both of them came back from Paris in 1960. That's the year I joined the Tata Institute. So when they came back, they both ran seminars on things which they had learned recently in Paris. So students at TIFR were exposed to the most current happenings in mathematics because of these people when they came back. Already Chandrasekharan and his colleague K.G. Raghunathan, who was also an important mathematician, they had already exposed students to many different things. But these people, when they came back, there was a, what should I say, a change, a jump, the whole thing. But even before they came, of course, they themselves got exposure to very excellent mathematicians from abroad, from France especially, and Germany, all first-rank mathematicians, well known. They all came to give only to nothing but there's no mathematician of importance in their subjects, but they still came to Tata Institute and lectured to graduate students. And graduate students got exposure to some really modern and very recent developments in mathematics of great depth. And that is what helped Narasimhan and Seshadri to write very good theses even when they were in Bombay, and later on to tackle problems which are really important and current. So, and when the two of them came back, they started collaborating actually in mathematical work. And in 1965, they published a paper about vector bundles on Riemann surfaces. No matter what, it had a tremendous impact. It was published 50 years ago, and last year, in fact, at the Chennai Mathematics Institute, they had a conference for the 50th, for the Golden Jubilee of the theorem, and lots of Westerners, American and European mathematicians came for that. Seshadri and Narasimhan, it's known as the Seshadri-Narasimhan theorem, which is well known, and it's one of the most important theorems in the entire theory of moduli of vector bundles, as it's called, and it's a very basic theorem. So that is, it certainly established a big name for the Tata Institute at that time. If you look at the pre-independence era, many of those mathematicians whom I mentioned were also very good scholars. They knew a hell of a lot of mathematics. But that's no longer the case now. Some of the, why has it happened? In some sense, our scientific leadership in the 50s is responsible for this, or even earlier. They recognized something. They thought Indian scholarship was becoming very arid. There's no original work being produced. People are always commenting on earlier work. Even the great Shankara wrote only commentaries on Upanishads and Vedas. So what was happening? Maybe this focus on too many things which are old and not trying to think for yourself was spoiling us. So they decided we should not encourage scholarship. We should rather start encouraging original thinking, which on the face of it looks very good. And also, if you look at the American example, it seemed just right. You saw this in the American graduate schools, so people turned out, perform excellently in their own area, but they have very little scholarship outside. And this example, we thought we could repeat here. But what was forgotten, or probably not adequately appreciated, is these students coming out of American graduate schools were guided by great scholars who came from Europe. Thanks to the Nazi atrocities, they had all moved to the US, and they had that guidance, and those guys were great scholars, so they could focus on some important problems and guide the students to that, and let the students develop into good scholars afterwards. That possibility was not available here in many places. Nevertheless, we had an urgency to grow science, so to speak. And so we had to recruit faculty which was not up to the mark very often, and it naturally had a slow deterioration in standards, and scholarship was not encouraged. And this trend has to change. If we want sustained high performance, the Tata Institute will become a flash in the back, a flash in the pan if it's not, if scholarship is not sustained. And the strength of Tata Institute even now is scholarship is sustained. The graduate school exposes students to many different things and lets students take their own decisions about problems very often. That is what made Tata Institute into a great success. And to some extent, all the successful models we have in the country are of that kind. But large majority of our universities don't pay any attention to scholarship. This quick fix PhDs won't get us anywhere. This has to change. And this will change. One of the things that has been contributing is the way UGC recruits or promotes its norms for promotion and so on. Number of papers, various numbers are important. Citation numbers, this, that, and so on. All of that doesn't make any sense in my opinion. At least in mathematics, many of these things are. See, it is the lazy person's device. You don't want to look into the person's work and make evaluation. Maybe you are not even capable. So what you do is substitute with this numerics, which are totally meaningless. You can write the number of publications of someone like, take an example like Gauss. His number of publications for his stature and so on is very small. And if you were to be, he wouldn't be made a professor in one of our universities to do that. So that's the kind of criteria you apply. It's the whole thing is absurd. This has to change. Somehow there must be given greater value should be given to scholarship. And in recruitment, it shouldn't play such an these numbers, the number of publications and so on should not play the kind of role it does now. I don't think I have any alternative suggestions which will solve problems overnight, but one has to pay attention to this and think along these lines. Well, one of the problems I mentioned this business about our dependence too much on old things. In fact, this has been with us for a very long time. Even Kalidasa has to lament. In the prologue to Malavika Agnimitram, he says, Puranamityeva nasadu sarvam nachapi kavyam navamityavadyam. Just because something is old, it's not great, nor is something new necessarily not unworthy. That's what he says. He felt it. Someone like Kalidasa felt it. And so that tradition continues, and unfortunately we still hark back to the ancients a little too much. We should stop that, and we should not bother. We are now inheritors of science from everywhere. We are not inheritors of just Indian science. Why bother about what Indian scientists did thousands of years ago? Okay, they did great things. You acknowledge that, you say that, by all means. It gives you some pride, welcome. But beyond that, to suggest that everything was known to them, plastic surgery was known to them, that kind of thing is really ridiculous. It actually is counterproductive. The past becomes a millstone around your neck rather than a foundation on which you can build. I hope these things change and we have a healthy attitude. Another thing that has been happening is the autonomy of institutions is being corroded progressively. I think the ultimate method will be to trust the academics themselves and give institutions real autonomy in making decisions. You can make your rules about how much salary you give, how much, all that kind of thing, yes, but what is the academic qualifications you need, the faculty should be the ultimate deciding factor. You can draw broad guidelines, but you cannot make the kind of micro management that UGC recommends. I will end with that. Thank you.